Hi, I'm Idan Achitov, and I'll present our work, Self-Supervised Learning for Domain Adaptation on Point Clouds, done in collaboration with Chagai Maroon and Gal Chechik. Point clouds are popular 3D data representations for objects, people, and scenes. Several deep architectures were developed for point cloud classification and segmentation, including PointNet and DGCNN, and they achieve high accuracy when trained with enough data. However, high-quality labeling is often costly and time-consuming. One possible solution is to use unsupervised domain adaptation. In unsupervised domain adaptation, one trains a model on a source distribution and uses it to classify data from a different target distribution. Unsupervised domain adaptation can be used in sim-to-real setups, training a model on a simulated source data where labels are easily obtained, and testing on real-world data. Here, we propose for the first time a technique for domain adaptation based on self-supervised learning on 3D point clouds. Our architecture has a shared feature encoder and two task-specific heads. The first head is for a supervised task on source domain samples, where we introduce supervised training procedure called point cloud mixup, PCM. The second head is for a self-supervised task that can be applied to both domains. Here we introduce a new SSL task called Deformation Reconstruction, DefRec. We now describe these two components. The first component, DefRec, is a simple auxiliary self-supervised learning task. Given a shape, deform it by dislocating some of the points. Process the deformed shape by a neural network, and train the network to reconstruct the deformed shape. But how to deform the shapes? We propose three deformation families: proximity in the input space, semantic similarity, and using existing sampling protocols. As a separate contribution, we also suggest an alternative for the standard training of point clouds motivated by the mixup method on labeled samples from the source domain. We call it point cloud mixup, PCM. Assuming a classification task and n points per shape, we suggest the following protocol. At each iteration, sample two shapes from the batch in a formula at random. Sample a mixing coefficient lambda from a beta distribution. Form a new shape by sampling lambda times n points from the first shape and 1 minus lambda times n points from the second shape. And finally, assign to the new shape a label based on the convex combination of the original shape's labels. We first evaluated our method in a classification task using the PointDA10 dataset. This dataset consists of three subsets: ModelNet, ShapeNet, and ScanNet, all sharing the same 10 classes like chair, table, and bed. ScanNet is an RGBD video dataset of scanned real-world indoor scenes, while ModelNet and ShapeNet contain shapes from 3D CAD models. In the table, each column corresponds to a pair of datasets, one for the source and the other for the target. DefRec with and without PCM outperforms all baselines in 5 out of 6 adaptation setups. With PCM, DefRec improves by 5% compared to the best baseline, and improves significantly on sim-to-real adaptations. For evaluating the applicability of DefRec and PCM to point cloud segmentation, we designed a new benchmark dataset called PointSegDA. It is built from a dataset of meshes of human models proposed by Maroon et al., which consists of 4 subsets: Adobe, Faust, MIT, and Scape. All subsets share the same 8 classes of human body parts, such as hand, feet, and head, but differ in point distribution, pose, and human identities. DefRec, either with or without PCM, achieves the highest mean intersection over union on most adaptation setups here as well. To conclude, we tackle the problem of domain adaptation on 3D point clouds. We provide 2 novel contributions: DefRec, a novel family of self-supervised pretext tasks, and PCM, a new training procedure for 3D point clouds based on the mixup training. We demonstrated the benefit of our method on several adaptation setups, reaching a new state-of-the-art results. Thank you for listening. Paper, code, and the new dataset are available at this address.